function generator and oscilloscope, we have dealt with DC signal so far, and DC signal is a continuous flat value of a voltage, and given your resistance, there is a continuous flat value of current that flows, right? So hence we we calculate or we measure or we simulate a DC circuit, we get one number, some volts, 5 volts, 9 volts, 10 volts, whatever volts. We're using 9-volt batteries, so 9 volts. And in response, we get current, right? So whatever network we have, whatever analysis we do, we get in a DC circuit, we get certain uh, current, some milliamp, some microamp. But when we are dealing with AC circuit, the idea is the basic difference is that AC is alternating current. The signal is alternating. The signal is not a continuous value, but signal is, and that signal can be voltage and that signal can be current. The signal, now the word signal when we use, we are talking about that value of voltage or that value of current, but it has more properties to it than just being a flat constant value. And that property is that it is changing with respect to time. It is changing in time. So if its maximum is 2 volt, which would mean either it is from 0 to 2 volt and going 0 to 2, again 0 to 2, or it is peak to peak 2 volts. In that case, we would say, okay, it is going from -1 to +1 volt. And it's alternating between these two maximum values. Now, how fast is it alternating? That's what would give us the concept of frequency. That is it going from say -1 to +1 in 1 second? Okay, so that's time, but that's not frequency. But then from time we get the frequency, right? 1/time is frequency. So how fast is it moving? That would be the frequency of a function, a frequency of a signal, right? Now, if something is alternating, if there is one variable which depends on another variable, like I'm saying it depends on time, then those variables, bunch of variables come together to create a function, right? In maths, we have a function, x-axis and y-axis, exactly the same thing. So the equipment that can generate that kind of signal, we call it a function generator, right? In very simple terms, what it does is it creates a signal, voltage or current, which would have certain basic properties that we define, that you will define, and that signal will start following those properties. And the fundamental property would be the voltage, right? The maximum voltage. We would define what would be the minimum and what would be the maximum, and we'll define how fast it would go through those two values. Right? So let's take a look at how do we make those uh, signals and what are some basic ways of how we look at those signals or manipulate that signals. Now, when you input a signal to a circuit, your circuit would do something. I don't know, maybe it's a circuit to uh, reduce voltage divider, maybe it's a circuit to amplify a signal, whatever that circuit do. So how do we know what is the circuit condition after going through certain circuit? We use machine called oscilloscope. So oscilloscope is which would measure that signal at any given point, at any between any two given locations, we would measure the signal, and oscilloscope would exactly trace that signal with respect to time on its screen. So for this lab, again, we would have needed these basic things, function generator, oscilloscope, and everything else that you have. But these are expensive equipment. We don't expect you to buy these for yourself. But we have some online variations where we can look at those concepts. So let's go through basic concepts, what we do. So when we do AC analysis, alternating current, there are these two basic devices, function generator and oscilloscope. Everything else is there already. You have resistances, you have capacitors, you have inductors, you know them already. Now, in a function generator, it would, it's, we are replacing DC power supply with the function generator. So DC power supply was giving you a continuous voltage, but now when you say function generator, this is going to give you an AC signal, right? So when you have it on your desktop, your lab, your wherever we are using, it has bunch of controls in the front, and there are places where we plug in our BNC cables in that. And those cables themselves have resistance. Now, those cables run from system to your circuit, from function generator, and similar from your circuit to your oscilloscope on the output side. So this is just basic idea. It has a positive and negative side. An oscilloscope is again another device which would display your signal. Okay, if I ask a simple question, what is our signal? How would you explain the signal? What is the DC input? So in our circuits, we have dealt with DC input. What was DC input?
Is it the battery?
Right. So what does it give to your circuit?
Voltage.
Voltage, right? So it's your input is voltage. Now, in AC signal, what's the input? In AC signal, what is the input?
It's a current source.
It's again a voltage.
Oh.
But what's the difference? I don't want to put Carlos on the spot, but he's replying. Nobody else is replying today. Guys, are you going too fast? Too slow? Monday is not a good day for us? All right. So, okay, anybody, what is the fundamental difference between a DC signal and AC signal?
The current.
DC signal is a constant. AC signal alternates.
Exactly. Who said that? Sorry, I don't see all the pictures on my screen. Gabriela, was that you?
Yes.
Good answer. Very good. So what is added on in an AC signal? That it is continuously changing signal. Alternating current. Alternating is the answer. So it has a waveform to it. So we are dealing with waves now when we are dealing with AC signal. Up and down, up and down, up and down. So hence it says display plots of such signals on its screen, because it is not a straight line now. Now it is changing. And that's what we need to measure, because in that signal, there are a bunch of things we need to measure. We have to measure amplitude of voltage at any given time. We have to measure peak to peak voltage, highest to lowest. We have to measure root mean square value of the voltage, root mean square. We have to get the root mean value. We have to measure frequency. We have to measure period. We have to measure phase shift. If there are two signals, we have to see how far or how different are these from each other. So these are all the basic parameters which you measure with an oscilloscope. Now, the handout talks about Appendix E. I'm trying to get my hands on. I asked the instructor who taught previously. I'll post it online. But this was more focused on if we were doing it in classroom. But my goal today is to give you basic introduction of the operations. Now, oscilloscope gives you representation of whatever we have input into a circuit and whatever our circuit has done to that signal. Right? So you can put oscilloscope at the input also. So you'll get what you are inputting. But then during the process of that circuit, it undergoes maybe amplification, it undergoes, I know you haven't, probably some of you have never heard of these words, amplification and phase shift and all those things. But bear with me. These are things that happen in a circuit. So oscilloscopes helps us look at the values in the circuit at any given time for the signal that was input. So think of it in a way that if you were, if you have a sort of a simple circuit, if you are dealing with your cell phone, for example. So what you get is an electromagnetic wave that comes to your phone, but what you hear is voice, right? You are hearing voice, or you are seeing each other like we are doing that. So this signal has gone through many changes, many steps to get to you looking at me, you're hearing me, I'm looking at you, I'm hearing you, right? You are sitting in your bedroom, I'm sitting in your bed, in my bedroom, and sorry, I was going to say I'm sitting in your bedroom. That would be very bad. So you're sitting in your bedroom, I'm sitting in my bedroom, but there are signals that are undergoing changes. So oscilloscope can tell us at any point what is the shape or what is the different values of all these things which are given here. So that can tell us if our circuit is behaving and doing what it is supposed to do. All right. So in an oscilloscope, let me show you a nice example online, which we will be playing with today. So you can do it right now. The website, I'm sharing the website in the chat. It's academo.org/demo/virtual oscilloscope. Let me share that in the chat so you can pop that up on your screen as well, because I would want you to do these things for this lab using this oscilloscope. It's virtual oscilloscope. All right, everybody got access to this thing? All right, so I'll be shifting back and forth between this and the handout. Now, what are these things here on an oscilloscope? There is y-axis, there is x-axis. Y-axis is the whatever we are inputting. So we are inputting voltage. So it says sine wave, amplitude 5 volt. Can you see that? Alejandro, can you see that? Oh yes, Alejandro is going up and down. Fantastic. So there's a bunch of input signals, right? You can generate just a signal, or you can, if you have the equipment, you can switch on to line input, which would be your 2 probes that are going into your circuit. So I'll just stick to sine wave for now. And because you want to see what is all this given on here. So here's the signal of voltage. So what's happening? Voltage was 0 here, and then it went up. Sorry, it's not 0, it's -1. This is 0 axis. Then it went to +1. Then it went down again, crossed the 0 point, again went to -1, and kept on going up and down, up and down. Now, I did some cheating. I aligned this to be going up, down, and up, passing this some 0 value here, some 0 value, because yeah, I didn't make it any special value. I just tweaked it to come there. How did I do that? I'll show you. That's one thing. The other thing which I did, I cheated and I made this minimum value and maximum value to be at -1 and +1, right? I could change that also. How do I change that? I can, number one, I can make this frequency bigger or smaller. What is the difference between two frequencies? If one is high frequency or low frequency, if it's audible frequency, what's the difference? Anyone a musician in this room? Musician. Do you have any musician? Do you have any singer? Carlos, are you a musician? Yes. Okay. Carlos, tell us about frequencies of your instruments.
Well, a higher instrument, like instruments with more, how to say, like with a higher frequency tend to sound like more what's the word? Like with more
Holes,
treble.
more treble, right?
Yeah. Yeah.
Yeah.
Dr. Iqbal?
Yes, sir.
Yeah, I have gotten the access to the lab. I have, oscilloscope and signal generator in front of me. So
All
I
right.
can
See,
demo them today if you want.
but yes, definitely, we would want you to do that. Hold on a second. Let me just show them online demo, and then we'll come with you. All right, Mansoor?
Yeah, that's okay.
All right. So while we were sitting in our rooms, offices, wherever, Mansoor was trying his hard to get into the lab to get a real oscilloscope, and he's going to demonstrate things that I'll just show you now. Very good. Mansoor, just hold on with me, and then I'll tell you when to start. Mansoor, I'll tell you when to start. Let me just go over
Yeah,
some
I'm
of the
here.
basics
You
of
can.
oscilloscope.
I'm here.
So frequency can change the tone. One would be more treble, one would be more bass. If you are into singers, singing, music, musician, you have to uh, tune your instrument. So you see what I'm doing? I'm changing the crossover points. So now here, when I put 500, I want to do it 500. It's gonna be, let me do it manually. So that's right here. It starts at 0, goes to max value, goes to min value, and goes to 0 before going into another period. So it's right sine wave in 180 degrees, right? And over and over. So you can adjust frequency. You can adjust gain. Gain is y-axis. Here I put the gain 1. If I do this, you see what's happening? It's going up, 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 up. Bigger and bigger signal, smaller and smaller signal. So we decide with our function generator what kind of signal we want. You can change the gain of the by changing just what is the division of seconds, how many seconds per division you want. So 1 millisecond, 1 over the time gives you hertz, the frequency. They're all connected with each other. Or you could, so it's the same thing which I did with this scale, with this slide bar, or I would have given exact values directly into the system, right? So I say, whatever you decide, the system will put that many volts in one division. Now, we here I cheated by giving this value and then aligned it. We could have been working with some odd frequency, say 556, and it would show it. But now it may not be aligned. So you can, and all of these things we do in oscilloscope. So I could have done the offset and adjusted it to whatever level. Now, what are we doing? We are not changing the signal. We are changing its representation, right? So we can then, if you have two signals, input and output, then we can align them and we can compare them. We can compare them how much the gain has changed. We can compare them if the angle has changed between them as well. What we call as phase shift. So we can do adjustments on horizontal and vertical offsets with this thing, right? This same thing which I'm going to share with you in the handout. All right, let's go back to the handout, and then let's go through this some basic theory, and then we'll get to the lab. All right, so what does an oscilloscope do? Oscilloscope, like shown here, it can be a continuous signal, or it may be a signal where we uh, have have two voltages. So then you would see the relationship between each other. But more often we have voltage versus time. So we have the signal with respect to time that gives us how is that signal changing. All right, so we use two inputs. So we use one signal, and then we may have we have two cables, two another signal. So those two cables make one channel, other two makes two channels. So we can input two channels to the oscilloscope. And simple idea, I just told you that you may want to compare two signals, input signal versus signal at any given point in your circuit. So then you can trace those two signals and see the difference between those two. Bigger, expensive scopes would have more channels in them as well. Now, we have uh, the signal that I was showing you, it was a signal which is analog signal. It is changing smoothly many values. But then there are digital signals which are one value changed to another, 0 and 1. That also can be done on oscilloscope. In that case, we just change it and we say, okay, digital signal. Now in digital signal, there are similar concepts, but slightly different, because now what we would have is what you call duty cycle. How much between one high and low, how long it stays high and how long it stays low, and what is the difference between what is the high voltage and what is the low voltage. So that would be the case in case of they take you back and show you they had that online thing. Let me show you when we take back. There is a digital setting there also. So here we were doing sine wave amplitude 5 volt, and then it says square wave amplitude 5. So square wave is the digital signal, right? Same concept, but now you don't have those intermediary values, you have up and up. So that then has different ways of how we explain our signal. All right, let's switch back to our handout. All right, so what do we measure? We have to know what is, when we say amplitude, what does that mean? And when we say peak to peak, what does that mean? So when you say amplitude, we are just looking at the central line, center baseline, which is the mean position of the signal. Now, when you say peak to peak, then we go to the minimum, most, and minima and maxima, and we measure the signal between those two, and that's what you would call as V with subscript PP, which is given here, VPP. VPP would be voltage peak to peak, right? But if it just says voltage or VP, that's normally what is the amplitude, which is with respect to the baseline, with the respect to the center line or average line. So here it shows the difference. When you say VP, we are just taking it from this middle line, but when we are talking peak to peak, we are going from the maxima to minima to see the difference. All right, so Mansoor, can you walk us through the handout with the actual microscope? Mansoor, is he with us? All right, yeah, Mansoor is here. Mansoor, can you show us a few things on the actual
Yes,
scope?
Dr. Iqbal, I'm here. Can you see me? Hi, everyone. I'm in the lab right now. So I brought a webcam. I think it'll be easier for me to show you guys using that cam. Just a few seconds.
All right, while you do that, let me take a screenshot to capture the
Uh,
attendance today.
I think you can see me right now. Yeah, you should be able to see me. Okay, I'm gonna fix this somewhere. So just for now, um, yeah, this should be good for now. Okay, so when I show you the actual, circuits and everything, it should, I'll show you guys like with the movable camera. So, okay, I'm in a different computer. Apologies for that. Could you actually like show me the, handout, because I don't have it at hand right now.
Yeah, sure. Let me share the header. All right, yeah. Just let me know when to go up or down.
Okay, there should be a page with a circuit on it, like that we have to, use our signal generator on. So could you show
Oh,
me?
I was saying, just show them where does the thing, like
Okay,
connector goes, what place.
okay. So first of all, a few things that I need to show you is, okay, so what you have right here is, this one is a oscilloscope, and this right here is a, sorry, this right here is a signal generator. So if I turn this on right here, um, okay, this one's not connected to a power source apparently.
It's okay, even if you don't get signal, that's perfectly fine. But just show them how we plug in things and how do we connect things up.
Okay, so
Mansoor,
yeah,
even if you cannot show the actual operation, that's fine. But just show it, close it up so they see what are the buttons and what are the different settings and where do we plug in the cable and all that things. All right, show them BNC cable. BNC cable on one end and a couple of alligator clips on the other side.
just a few seconds, just if you could wait. I have a bit of setup to do.
So
So as you can see right here, this is a signal generator. So this right here is where you get the output from. Okay, I'm having a bit of, so yeah. So this is the thing that you get the output from. So let's say you program this to, let's say you set it to sine, so it gives a AC, the sine signal. This one gives a triangular wave signal, the RAM. Square basically means that the values that you get from this are like flat values, like let's say 5 volt positive, 5 volt negative. So it basically means that it will always be 5 volt positive or 5 volt negative. This is the square signal, but in sine it will go from like it will vary from the 5 and -5. It will vary from there, and arbitrary is basically to simulate a noise like signal. So this is where there is also this right here to control the signal frequency. As you can see, like right here, megahertz, kilohertz, hertz, and millihertz. So if you select one of these and then input a value, then it will basically input like use that signal as its output. And the rating is already given right here. As you can see, 20 megahertz. It should be inverted in your screen, but if right here it's written 20 megahertz, which means that the maximum frequency that it can output as a signal generator is mm, you know uh, 20 megahertz. This dial right here is basically used to uh, make changes to the output that you get from this. So let's move to the circuit right here. So this is a very basic circuit. It's basically,
Show them the alligator clips.
yeah, okay. So as you can see right here, I, I've
So,
used like these two alligator clips. These are where the output comes out from. This is the red one is the positive and the black one is the
so
negative. So
just follow these two cables and go through. Just follow from the alligator clip and show the camera. Wow, just take it slowly from the alligator clips.
So as you can see, this right here is the output for this signal generator, and the output for this signal generator is the input for the circuit.
Hold on, Mansoor. Hold on, Mansoor. So we call this BNC cable. So this is the BNC on one side, and now Mansoor, take us down. So this BNC on the other end. No, you went too far. Show me where it splits into two cables. So BNC comes and then it splits into two, red and black. And red and black have then alligator clip at the bottom. So alligator clip, then you can connect to the cable and connect to your circuit. And that's how you would bring in your oscilloscope. And in your circuit, then you would know where to place which cable goes where to detect the signal.
Yeah. There is a
But
functional signal generator right here. I can show you guys that one, but it's a bit far away. I have to move the computer a bit.
it's okay, it's okay. Let's continue on this one. There's plenty to learn from oscilloscope. So, you mind if I uh, bring the handout up?
Yeah, you can. Yeah, no
Just
problem if you bring out the handout.
give me so we can go through and they know that where are we right now on the handout. So this is one BNC is one channel. So you would know on the oscilloscope itself which channel you are using. So once you get that in, now it the handout we are showing you oscilloscope, but it's talking about function generator. But they are both of same things. Only difference is one is sending the signal out, which is function generator, and the oscilloscope we are sensing the signal. We are looking at the signal how it looks. But otherwise, the cabling is the same. Now, in your circuit, you would start with function generator on one side, and you would do these settings, right? Sine wave. I showed you how do you set sine wave. 50% duty cycle under square waveform, a setting for your signal. And on the oscilloscope, then you would say, okay, X1 attenuation. Many times signal is too large and you want to make it smaller so it fits your screen. So you say, okay, same X1 attenuation. Auto set again, which would make the signal fit your screen on your oscilloscope. So you do auto set. Basic operation, these are you press the specific buttons of whatever you want to build. We want to build sine wave, we push sine. We want square wave, we push square. We want triangular wave. So those are the specific things which are given in the lab of what you need to do to get the specific signal from your function generator. And then there are also options where they say, okay, what kind of amplitude are you inputting? Amplitude, or are you inputting peak to peak? So you'll tell the system, okay, this is what I want. You would exactly the same way I showed you on the website. Then you send the frequency, you see offset of how far up or X or Y axis you want it to be. you want to align it basically to your gradings which are given on the screen. And duty cycle, again, what percentage does it stays on and what with respect to the total signal. And okay, so you'll do auto scale so it stays within the screen. So these are essentially the things which with the just straightforward. You just follow, you do it on the system and you see these things happening. You set the frequency. Now, obviously, these are things which we want to, Mansoor can show us how and where is that button. He was showing you the buttons already. Mansoor, you want to make it larger? All right, so what you guys can do now, pin the video of Mansoor, and that will make it larger for you.
Yeah, so as you can see, I've already attached the, channel 1 and channel 2, probes for the circuit. So here it is shown like this one right here, channel 1 has a pink band to it. So the channel 1 right here is this one right here with the pink band. As you can see, this one is connected to this first resistor. And this one, which has nothing on it, is also connected to the second resistor. So if I were to, let's say input a signal into it, so this one has its own preset, signals and presets and everything, that this will measure a certain frequency within a certain range and everything. So it might not show up in the signal generator immediately, like in the oscilloscope immediately. So what you need to do sometimes is use this function called auto set or auto range. So this for this oscilloscope right here, it's this function called auto range. So this will immediately find out the maximum and minimum voltages and display the voltages here accordingly. Um, if there's a running one right here, I can show you guys that one. Um, can you? It's difficult. Okay, I need to move the PC a bit, just a little. So.
Okay, yeah. So do it, we'll wait.
Okay, so yeah, this. As you can see right here, this is a oscilloscope which is working. So if I were to, let's say this one does not have an input signal to it right now. So if I were to, use one, give it an input. So what I would initially have to do is use this auto range button right here so that I can immediately get the value, like the signal being shown here, and I can, show you guys that how it works. I have to do a bit of setup for the signal generator so that I can show you like how it actually works. Like I can show you guys like it working. I need a few minutes for that. But
That's fine. Let me go over the handout a little bit more. You go ahead and you do it, and I'll take them through the handout a little bit further. All right. So when you set the function generator, you decide, okay, square wave, 4 volt, peak to peak, 2 kilohertz. So these are the settings, typical settings that you would have done in this, uh, what do you call, in this lab. And once we are ready, we push the measure button. And that's where we get a bunch of options where we can find uh, voltage peak to peak, frequency period, max voltage, min voltage. You have to make sure you are on the right channel where you are measuring. So all the things that you have set up on the function generator on oscilloscope will be measuring those. Now, this is where your circuit would make your signal undergo changes. Is it an amplifier? Is it a band pass filter? Is it low pass filter? So whatever the conditions, that signal will come after undergoing those changes. So those are the values that you would measure from oscilloscope. And this is where we would have done some projects, different students doing different projects. But the idea is that we would set frequency, we would set sine waves, we would set max min voltage and duty cycle, and we would then see what is the signal coming on the oscilloscope through your circuit. So here we were using, up till now, we are using it as it is, right? Just the function generator and the oscilloscope. So you essentially get what you are inputting. And this is where we then, uh, well, these are the settings which you would do. Now, here's the thing. We are not doing it. So we want you to do A, B, C, D, all 4 of those on that virtual oscilloscope. There, the only option is sine wave, which is perfectly fine. But when you do all this, you take a screenshot, and that screenshot will undergo this heading of your lab. We don't have max voltage, min voltage, but we have the voltage that you can set there. All right? So use these values for input into that and take screenshot, and that will go into your lab. Right? Everybody gets that?
Yeah.
All right. So in the same uh, website, they had these vertical controls where you can define what is voltage per division you want to set, right? So your voltage is one thing, and how you visualize, that's how you set it, right? That's according to what is, maybe we have 2 signals and we want to put them on the same scale to compare them. Now on oscilloscope, you can move your cursor at different locations. At every location, you can get the cursor value, or you can use that cursor value to change the display as well. So you can pick that place, and you can set the display to maybe make that as 0 voltage value, and everything else then gets adjusted accordingly, up or down, right? So that's again to compare a signal or to see a signal value at a specific voltage. So that's on the cursor control and what you can do with your cursor. Now, on acquire, we have a signal that we can basically machine is a digital system. So it converts to digital, and then it puts the signal as waveform. So we can, within the oscilloscope, we can adjust between 3 modes. One is normal sample mode, where we get it reconstructs the signal into evenly spaced way. Or we can detect the highest and lowest values, and then it takes those 2 values and rebuild the wave according to those 2 values. Or we can ask it to take several waveforms and then average them out and show us the average. They all have their own pluses and minuses when we are doing the actual measurement in a circuit. But for us, we'll stick to normal sample, where it takes the evenly spaced and just reconstructs the waveform that's quicker, right? So and when you do advanced projects, you will know that in some cases you might want to use average mode than normal sample mode. because your input signal may have some variation over time, may have some uh, vibrations, maybe have some error. So you want to take the average mode in that cases. But this is a simple lab. Here there's very least interference in your circuit. So we'll just take normal sample mode in that for this one, right? All right. So we whenever you do that, we have to save the image. This is straightforward. On your computers, you know how to take screenshots. But on Oscilloscope, there is a way where we do save image button and then we define it. Where do we want it to go? And they all have USBs now, the modern ones. The old ones, they are used to be very difficult ways of how to do that. But yeah, save image. If you're doing online, you can just take screenshot. That should do it. And by the way, all the oscilloscopes we have, they have an interface with computers. So yeah, that's straightforward. All right, so we are building a resistive circuit now. Very simple circuit. It has two 1 kilo ohm resistors, right? The only difference between what we have done before and what we are doing now is power supply. Instead of using your 9-volt battery, we would have used a function generator. And a function generator, these 1 VPP at 1 kilohertz. I hope by now all of you know what does that mean. Anyone who does not know what does that mean, so I can go over. So you know what does 1 VPP mean? 1 volts, 1 volt. You will have to say the whole thing. Manuel, what does 1 VPP mean? 1 voltage peak to peak. In AC signals, you will not say 1 volt. You would say 1 V peak to peak, 1 volt peak to peak, always. You will write it like that. You will say it like that. Why is that? Robert, time to go, man. Sleepy, right? Okay, we'll wrap up right soon. So you'll always use PP and we'll always say PP. It will tell us peak to peak, the minimum and the max value. And at 1 kilohertz means the frequency, right? So that tells you it's an AC signal. So this is the basic circuit. When you build the circuit, in our case, between this point, let me use the annotation. All we will do is, this is the very important thing. What is this thing?
Wow.
Ground. Ground is our savior, because what we will do is we'll put a function generator here and the other cable will be grounded. And here is what you will be using to generate your function. And on this side, this is V out, right? So your oscilloscope will be red light here and green and the black one here because it's ground. So all you have to care is you need to get the red ones right at the right place, because the black ones are all going common with the ground. So if you look at it this way, then your circuit is very simple thing. Your circuit is just this, two resistances, and then your crocodile thing. What is that? What are these things? Alligator clips. I said crocodile. Nobody's paying attention.
Alligator clips.
Alligator clips. So alligator clip comes to one resistance, alligator clip comes to other resistance. This is probe on this side. And these two are just grounded, but they have to be the same ground as your resistance. So they are at the same value. And this will give you a simple signal. Get your signal in and get your signal on your output. Peak to, oh, Francisco said peak to peak. All right, thank you. All right, so the circuit may look uh, complex, but you have to just follow your grounds. It makes it very easy to input the signal, very easy to read the signal, right? So essentially, it's just taking you through the same thing, that we will use resistors. AC component is the sinusoidal wave applied, and two probes, both channels. Now, why are we using both channels? One is because we are comparing the input signal with the output signal. We are measuring what's coming from your function generator, and we are measuring what is coming out of your circuit. So hence, all right, yeah, now. So hence we have this is channel A1 and channel A2. So these are probes of your oscilloscope at two places. So this one, channel 2 going to ground, this one on channel 1, the black one going to ground. All right, Mansoor, you ready? All right, so here again, you have to measure V in peak to peak, V out peak to peak, and the frequency. All right, let's see, where is Mansoor?
Yeah. So I'm having a bit of trouble with the you know settings and everything.
Just show us how would it look like. Don't worry about measuring the actual thing. Just show us.
So
This is the
okay.
circuit, it's a probe coming in, it's your alligator clip, and where's your ground, and how do we build this basic circuit?
Okay, so as you can see right here, there's a signal generator that's on, and it is connected to this circuit right here. As you can see, it's going into the VA and the ground, and it is being connected to this circuit right here. And this one right here, this oscilloscope right here is connected across this one resistor. Sorry, this one resistor right here. So what you would initially do is actually, go to the, after making the connections, is connect this oscilloscope uh, and press this button right here called auto set. So this auto set basically measures the input voltage, current, and the frequency of the input, and makes it so that it shows a few cycles here. So it will basically, change the division amount of time shown per horizontal division and vertical division, so that it can change. So right here, as you can see, it's set to channel 1, 500 millivolts per division, and 10 milliseconds per division. That means for every dot that you see right here, you will basically see 10 milliseconds of time pass, and for every vertical dot that you move up, it will move up 5 millivolts. So this is how you will see it. But let's say you want a output to be shown, like to show a very specific portion of the signal, then what you want to do right here is change the voltage per division. This is done by turning these two dials. So this will basically make the signal that is shown here wider or narrower. And second per division is basically like it'll this one changes the y-axis. That means it'll go taller or shorter. And second per division basically changes the you know it will make the signal narrower or shorter or wider. So that's how it basically works. Yeah.
All right, let me take the handout a little bit further. Meantime, all right. So the way we made that two resistance, we make an RC circuit as well, resistance and capacitor. So again, you set the source to 4 VPP, 200 hertz sine wave, and we measured signal coming from the function generator, and we measure the voltage across the output resistance R. This would look like the circuit would be like this, but when you build it, that's something like this. Again, you get to alligator once, function generator, ground, you bring your probe, channel 1, your probe for channel 2, and we measure the difference between those two. What does an RC circuit do? I know none of you would know, nobody would have taught you. So RC circuit would change the frequency, not the frequency, change the phase between voltage and current on the output. So when you say change the phase, what does that mean? This simply means that there will be the signal which if if it would have gone up and down together, now it is moving out of sync. It is moving out of sync. So the difference between two signals, input and output, is now measured in terms of angles. That how many degrees has the signal shifted? And that's what we call phase angle shift, right? So that's the word here. It's given phase. Let me just highlight. We are talking about this guy. And it's measured in degrees between the measured input and the output. If two people are going linearly, we can say one is going faster, the other one is going slower, and we can measure distance between them. But if there are two waves which are traveling, the difference between the two waves is measured by phase angle shift, right? Now, the two traces will give us if it's a positive number or negative number, because one signal, in case of, I don't want to get into capacitor and inductors, they have different effect on the phase angle shift. But the if the output lags, stays behind, or the output leads, moves forward than the input, they both are the things that we want to know, right? And that's what we would measure when we are measuring two channels, input and output, with uh, something like RC circuit or LC circuit as well, right? Now, that's when you plot them on top of each other, then we can find out exactly the angle between those two. So now, again, the basic idea is, let me draw it just simply so we can get any confusions out of the way. So if this was x-axis and y-axis, and this is, say, input signal, and then I say you measure the output, and your output is coming up like this. So basically, your output is now few degrees different than the input. So this is the phase angle shift. I'm just picking peak. I could have picked the minimum values also from uh, both of those waveforms. Do you see what I'm saying? What I'm showing here? Input signal and output signal. What does it mean for the have to have phase angle? It might have been a signal like this, which would have gone out of the phase, which is now lagging. So this is input, this is output. So now in this case, the difference would have been, how many degrees are these between here? Everybody sees what I'm doing here? All right, very good. If you don't, just raise your hand right now so I can redraw it or explain it further. All right, so this is where then we use the cursor to exactly figure out how far they are from each other. So we're not doing this, so I'll just skip through this part. After the lab, now you have to do PSpice, and you have to perform a transient analysis of the RC circuit. The same circuit that we got, you have to build it, and you have to do transient analysis. And it should look like this figure when you build it. right? So when you do the transient response, you would do the analysis where you would get, uh, you will need a V sine part as your source. Instead of DC, VDC, you get a sinusoidal voltage input. And this would require you to define the off voltage, the amplitude, and the frequency in all cases. Whenever you use VSIN, this is what you'll have to define. Mansoor, you want to take it from here, or you haven't seen this part before?
Dr. Iqbal, what did you say?
Do you want to go to PSpice from here, or
I don't have PSpice with me right now,
okay,
so
you're in
I
the lab.
honestly can't show you. I'm sorry for that.
Okay, it's okay. We can make a video afterward and maybe post it by these steps. But I want you guys to do, it's all explained here. Your VSIN values will be given, and then you would use that, you would tell it you're doing transient simulation by going into analysis step, setup, and checking transient button. Now, when you do this, you will adjust the final time and step ceiling. So just use these values. At this stage, I just want you to use these values. But it's in advanced stage, then you know what these things do and mean. And you will plot now two signals, the resistor voltage and the capacitor voltage. What you do is you again use voltage, you find voltage on resistors, and that be the V out node. Now in the plot, you would add trace, and you would, under the trace expression, you would do V in, V out. So both of them are traced together. And we haven't done the lab, but this is where you have to get the screenshot of how does it look like. Now, again, we haven't done, so we will not do this. So just remember this. I'll be posting the whole lab as it is, but you have to remember that this is part we haven't done, so we cannot do that. But you have to put the schematics, what you get from PSpice, on in your report, and you know how to save that. So basically, this is how it should look like. That's given in number 7. So with those values, those numbers, your plot should look like this. And here now you can see that how input has changed in amplitude from with this circuit, and how much phase angle shift has come between those two signals. All right, questions?
Dr. Iqbal, I can show them one last thing, like
Okay.
the things that I wasn't able to actually like show.
All right.
If you
Go
guys
ahead.
pin the video, I can show you just a few things. So as you can see right here, yeah. So as you can see right here, I have, I'm not using the signal from the signal generator right now. I'm using a signal from the oscilloscope itself. This signal is actually a test signal to make sure that the probes are properly connected or not. But this can, work to show you guys like how the oscilloscope works itself. So right now I have actually, changed things up a bit. Like I have used autoset, but I'm going to change a few things. Like I'm gonna change the vertical position and the voltage shift per division and the time per division. So as you can see, this is a very weird signal that you're seeing right now. This is because I've changed the things about voltage per division and the seconds per division and everything. So if I just press auto set, what will happen right now is measuring everything and then giving us a proper, view of the whole signal. So right now it says, in channel 1, it's 20 volts, which means that for every division, which means like every square that you see right now, this has a grid. So every square that you see, so if you move up the square, you'll see you'll see a movement of 20 volts. So since this is a 50, if you press measure. Yeah, I don't know why. Okay, so yeah, so I'm just gonna say, right, so if you see right here, it says 20 volts, so which means that right now, if we move up from this base to this right here, we see 20 volts, and then here's 40 volts, and if you see right at the top, it's 50 volts, and this right here is 500 milliseconds, which means that from here to here, 1 square, it's 500 milliseconds. So if you move from this point right here to the second point right here, it's 2 squares. So it means that 500 into 2, which is 1 millisecond. 500 microseconds into 2, which means 1 millisecond. So the signal that we're getting right here is a 50 volt signal, and the period for this signal is 1 millisecond. So this is how it works. So if you want to, let's say, change the height or width of the signal, what you have to do is select the channel. Since I'm running using channel 1 probe, so I have to change the channel 1's voltage per division. And as you can see, if I change it, it gets taller or shorter. I can make changes to this, to the vertical positioning of the signal in the oscilloscope using the upper dial right here. So as you can see, if I make this one taller, I can, put it down and then see better. And if I, want to change the time positioning of the signal, then I can use this one. And if I want to make it narrow or wide, I can change the second per division using this dial right here, this one. So yeah, this is a very awkward view, I know, but right, like focus on my fingers, as you can see, this one, this dial right here, this one changes the width of the signal, like how much time it shows. So this basically is how an oscilloscope works.